Hello, good evening everyone. Am I audible, right? Hello.
Yes, sir, we can start.
Okay, so we can start. Okay, so let's move into the first question of today. This is the question number 9 of grade 2014 Metallurgical Engineering. So this question states that a tensile specimen was deformed at a constant crosshead speed of 6 millimeter per minute. The strain rate at the start of the testing was 5 into 10 to the power minus 3 second inverse. uh, the initial gauge length of the specimen in millimeter was. So in this case we have to determine the initial gauge length, that is the L naught. So we have to determine the L naught values. Now what are the data are given to us? One is the crosshead speed. This is, let's say, crosshead speed is denoted by V and it is 6 millimeter per minute, and the strain rate at the initial, at the start of the testing, it is given. So strain rate epsilon dot, it is given 5 into 10 to the power minus 3 per second. Okay, so uh, anyone want to approach how to solve this question?
Sir, what is crosshead speed, sir?
Yeah, so crosshead speed is like, let's say this is your tensile specimen. So so my drawing is a bit bad. Okay, so let's say this is your tensile specimen, right? So when you are putting your tensile specimen in the in the machine, so there is a two holder, this, which grip this sample. This two holder grips this sample, and then this holder basically pull your sample like this it will pull. So these two thing, these two grip is called the crosshead. So the speed of this crosshead, that movement speed of of these two grip is called as that crosshead speed. So these are the grip. So now your that machine is basically pulling your sample like this. Like, let's say if this is a sample, so your machine will pull this sample like this. So now let's say this is the initial condition where when the length of the sample was L naught, that is the gauge length of your sample. Now after some times, let's say this crosshead moves up to here, and it moves here. So that means your sample will be a bit elongated, right?
Yes, sir.
Let's say this length is now become L. So now what are the now you understand, right, what is crosshead speed? V means the movement speed of these two holder or these two grip is crosshead speed. Yeah, have you?
Yes, sir.
Okay, so now can you try how to approach this question from the given data? How can we calculate L naught? What is the strain rate? So you know what is crosshead speed. Now what is strain rate? What is strain? What is the formula for the strain, for calculating strain? Anyone?
Change in length by the original length.
Yeah. So change in length by original length. Strain epsilon. Epsilon is L minus L naught divided by L naught, or you can write delta L by L naught. So this is strain, but strain rate is given to us, not strain. So strain rate is change in strain per unit time. That is epsilon dot, you can write as E by epsilon by T, or unit time. So epsilon dot is this delta L by L naught into T, right? So we can write strain rate in terms of L like this. Now v or velocity of the crosshead is how can we write this crosshead speed in terms of L? Anyone? From this two diagram itself you can say how we can write v in terms of L. So this is initial and this is final. So how much is the change? What is velocity?
meter per second.
Velocity is basically displacement per
Yes.
unit time, right? So what is how much is the displacement here of this crosshead? Right, initially the displacement was initially length was L naught. Now the length become L. So what is the displacement? L minus L naught,
L net.
right? And per unit per time, that is t. Let's say that after t times we are measuring. So this will be delta L by t is your crosshead speed. So v is delta L by t. So now if we put this thing, the delta L by t in this equation, what we will get? We'll get epsilon dot is equal to delta L by t into 1 by L naught. So what is the delta L by t? Delta L by t is basically v by L naught, right? So now from this equation we can calculate L naught is equal to v by epsilon dot. Now everything is given to us. V we know, but it is in the unit of 6 millimeter per minute. So we have to convert into in the second per second. So what will be it? So it will be 6 by 60 millimeter per second, right? So it will be 0.1 millimeter per second. So V is 0.1 millimeter per second divided by epsilon dot is 5 into 10 to the minus 3 per second. So your second and second will cancel out. So what will be the gauge length? Initial gauge length L naught. How much you are getting then? Right. So initial gauge length is 20 millimeter. Everyone understood up to this part? Anyone has any doubt? Okay. So the answer is 20 millimeter. This was a very simple question. So, means if people have any doubt regarding anything, any topic of this question, like tensile testing or any other terms you are not getting, or you have any doubt, you can ask.
No, sir.
Okay, okay, okay. So now let's move into the next question. Uh, so this is the question number 12 of GATE 2014 Metallurgical Engineering. So the question states that which one of the following refers to the ability of a material to absorb energy when deformed elastically? So option A is toughness, option B is fracture toughness, option C is resilience, and option D is hardness. So yes, Devendra, you are right. Answer will be resilience. So what is resilience? Can you draw the stress strain curve and just explain from this? Then what is resilience? This is the definition, right? Re- Definition of resilience is ability of a material to absorb energy when deformed elastically. So let's say if I draw the stress strain curve, how the curve will look like? So this is sigma, this is epsilon. So initially materials deform elastically, and then after that it starts to deform plastically, right? if it is a ductile material, then this stress strain curve look like this. If the material is not ductile, let's say for ceramic, how it will look? It will just have only elastic limit and then it will fracture. But for ductile material, it will first deform elastically and then it will start deforming plastically and then it will fracture. Right now, uh, from this stress strain curve, can you show me which area will be the resilience, or how we can determine the resilience from this stress strain curve?
Sir, we draw the vertical line that is from the yield point, and that region is will be resilience in the
Okay,
in this.
means this one.
Yes,
Yeah. So now what is the resilience then?
the area covered between that's the resilience, sir.
Okay,
This is the
area
area
covered by
between.
this region.
Yes, sir.
Yes, you're right. So basically, up to this point, your material is deforming elastically. So uh, the energy absorbed when deforming elastically is described by this area. That is your elastic limit sigma E and epsilon E. So your resilience is this area. So half into sigma E into epsilon E. This is resilience. Now, can anyone tell me what is the toughness and what is the difference between toughness and fracture toughness?
UTS points, sir. There is the two region UTS, and after that the
Okay,
from
let's say this
from
is
that
the, let's say, okay,
yield point.
let's say it is increasing and then it is decreasing and it
Yes,
is fracture here. So let's say this is the UTS. This is the fracture strength.
yes.
So now what is toughness? And for
So,
this material, fracture is happening here.
sir, we draw the vertical line from that. We calculate the area from the that region.
Particularly from where?
UTS point.
You are saying from this.
Yes, sir.
Okay, what is the definition of toughness? What is the
Maximum
definition of
stress.
toughness?
Maximum stress can bear before a fracture.
Now that is the definition of UTS. The maximum stress you are saying.
Yes.
The maximum stress in can deform is UTS. In the stress strain curve, this maximum point is UTS.
Oh, sorry. Sir, maximum energy it can observe before failure in elastic region.
Yeah, maximum energy or energy absorbed when material deformed plastically before fracture. Means before fracture, how much energy it can absorb, that is basically known as your toughness. So that means the total energy absorbed by your material. That means up to this point, not up to this point. Up to this point, it is deforming plastically, right? And then it is fracturing. That is, then it is broken into two pieces or like this. So then, what will be the toughness? Then toughness is basically this total area under the stress strain curve. This is your toughness. And now, if you can see this stress strain curve, let's say this is for ceramic. What will be the resilience here and what will be the toughness here?
The resilience and toughness will be the both in same because
Okay, in
it is
this case, it is
from
only
different.
deforming elastically. It is not deforming plastically, right? So in this case, only the resilience is important. Toughness is ability of material to absorb energy when deforming plastically without fracturing, right? So for this case the resilience is important. Uh, it is only deforming elastically, so this area will be the resilience of this material, right? And what is modulus of elasticity or elastic modulus? I think you have heard this term.
Stress by strain.
Yeah, so that means from, if I ask from this diagram, what is this basically? Stress by strain. What is it? From the diagram, can you just tell me what is this? What is modulus of elasticity? No, you are right. Stress by strain. Stress by strain means what? This slope, right? E is sigma by epsilon. So this is basically slope of this line, right? Got it. Similarly from here
Yes.
also. So this is elastic modulus. Now, what is the difference between toughness and fracture toughness? What is fracture toughness? Devendra, do you want to answer?
No, sir.
Fracture toughness, anything in your mind? What is the difference between toughness? What is toughness? Now you know. But what is fracture toughness?
Sir,
Yeah,
toughness, as you already told that maximum energy can observe in plastic region without failure, and the
yeah.
fracture toughness, from here the point it start fracturing. That is called fracture toughness.
But here also it is fracturing and this total energy we call toughness, right? But what is fracture toughness? Is these two things are same or different?
No, sir, different. But
Hmm.
sir, can you extend this graph from the point where we are calculating the toughness? Because after the UTS point, there is one point where we are calculating from the toughness. After that, this graph also extended in the case of making something like that. That area will be calculated in the toughness.
No, not really.
Okay.
Is it uh, something different? Concentrate on this term fracture. You have read the fracture mechanics from Dieter or some any other book? Fracture mechanics.
No.
Have you heard about crack propagation?
Yeah.
So there, this term is there. Fracture toughness. Remember now. Let's say this is your sample. There is a sharp crack is there. This crack length is A. Now I'm talking about fracture toughness. Don't move this thing. Okay, okay, I cannot erase it. Ah, so now, let's say if your sample has a small crack and the length of this crack is A, it may be of two types. One may be the edge crack or one may be the crack in the center. Or
Okay.
this is 2A. So now if you are loading your sample like this, how will be the stress line? So in this case, let's say this will be the stress line. Stress line will be here. So when it will come near the crack, na, so it will bend like this again because of the unavailability of the material near the crack. So the stress line will be bent like this. It will go like this. So what will be the situation here then? here the stress concentration will be very high near the crack tip, right? So the stress concentration will be very high near the crack tip. It is like similar like if you are having a water flow in a pipe, and then you are bending this pipe, what will happen? Near the bend region, more water will, like, it will go in the, it will bend and then it will then go, right? So similar, the iso stress line will be like this only. So here stress concentration will build up. So when stress concentration will build up, what will happen? Then this crack will start to propagate, right?
Propagate.
Yeah. So this basically, so let's say this is the your applied stress sigma. So here it will be something else, and here it will be some high value. That is basically given by stress concentration factor Kt, that is sigma maximum, that means sigma near the tip, near this tip, divided by the sigma applied. So this is stress concentration factor. This is termed as Kt. But uh, and fracture toughness is, the relation is K is equal to, this is y into sigma, this is applied, your applied sigma, root over of pi a. So this is the fracture toughness. Sorry, not this is the fracture toughness. This is stress intensity factor. So there is two term. One is K, that is stress intensity, and this Kt is stress concentration. So there is like almost similar looking like term, but the terms means different thing. So don't get confused on this term, because many time question may come like this. Here there will be a similar kind of term, and then it will, you will just confuse between these terms. So just keep in mind that these are the different things. So stress concentration is a different thing. Stress intensity is a different thing. Although they are related in some way, but the both terms are a bit different. So in case of stress intensity factor, this y is depend on the your geometry of the sample, and this sigma is your applied sigma, okay, and this a is the length of the your crack. If it is a edge crack, see, let's say this is your edge crack, so this length is a, okay. If it is a center crack, then it will term this as 2a, then this a is half of your crack length, this half distance of your crack length, okay. So this is your stress intensity factor. Now let's say when you are applying load, what will happen? Your that stress will get concentrated near the crack tip, right? Now you understand why the stress will concentrate on near the crack tip. You got this this point, right? Or you have any doubt?
सर एक्चुअली ना सर ये पढ़ रहे हैं तो मुझे समझ में नहीं आते तो छोड़ दिए थे.
अच्छा अच्छा.
हाँ.
So, but now are you getting that why stress is getting concentrated near the crack tip? Like just for the timing, let's say this is a pipe where water is flowing. So your water is flowing like this here. So here the water will go along a straight line path. Here also it will go straight. Now here also will get straight. But here it is getting hindered by this thing, right? So what it will do then? It will not accumulate there. So flow is there. So it will just bend its path, and then it will go like this. Again here also it will bend its paths and it will go like this. So what will happen then? Near your this crack, this is your crack, right? So near the tip, so what will happen? Near the tip, that stress intensity will be very high. So that is why means when you have a very sharp crack, na, so that time your stress will intensity will be very stress concentration means will be very high. If you think like this, that flow of water, then
Yes.
near this thing it will bend, and then so this line, like more number of line will pass through this sharp tip region. So that is why, let's say if you are applying sigma here, so now this is your crack, so very far distance from the this length, your stress will be sigma, but near the tip the stress will be very high. Let's say it is sigma max. So your stress distribution will be like this from the crack tip.
Yes, sir.
You are applying sigma, but your stress that is accumulated near the tip will be very high. So which portion will try to deform first? This tip region, right?
Tip region.
Because stress is very high there. So that is why it will deform and it will then propagate. If it is a plastic material or means ductile material, then first what will happen? That crack, because of the deformation, this tip will get blunted. Okay, and now when means that it will cross the limit, what will happen? Then again this blunted tip will also get crack. So again it will form a one micro crack. So this way basically this crack will propagate. Okay, so once the limit is reached, then what will happen? This stress intensity factor, which I told that formula I have expressed earlier, right? This stress intensity factor. So let's say this is pi a. So now this stress intensity factor, when it reaches its maximum value, when this failure will occur, like then it is termed as K1C, because this mode of loading is 1. That's a K1C. It will be 1 into sigma root over pi into AC. That is a critical length. When this crack will reach up to a critical length, then this your sample will just fail. That means when your the stress intensity factor will reach a critical value, when your crack propagation rate will be very rapid and unlimited, like the, very rapidly your crack will propagate and it will fail, that your sample will be fractured. So that critical stress intensity factor is termed as fracture toughness. So you got different kind of terms, right? One is KT. What is KT? What is K? And what is KIC? Now you remember? Now you can tell.
Sir, KIC is critical intensity factor. K is the
KIC is critical uh, intensity factor, stress intensity factor, or it is termed as fracture toughness. So both you
yes.
can. So it is basically known as fracture toughness, because at this point your material is getting fractured, right? So it is fracture toughness. And what is K?
Intensity factor.
Stress intensity factor. And what is KT?
Okay.
KT is here when your stress is getting concentrated here. So that means the ratio between these two, this maximum stress and this sigma. So KT is sigma max plus sigma. So what KT is showing? KT is showing what will be the stress that will be concentrated near your crack, right? This ratio is basically defining this thing. How much stress will accumulate near the tip of the crack. So it is called stress concentration factor. So there is three different terms out there. One is stress concentration, one is stress intensity, and one is the fracture toughness. It is like similar if you see this stress system diagram, na. So at this point, what you will call this is a sigma, just stress. But why you are calling this one UTS, ultimate tensile? Because it is a ultimate value or it is a maximum value. And why you are calling it a fracture stress? Because at this point your sample is getting fractured. Similarly here, when it is means a general value, that time it is a simply stress intensity factor. But as soon as it is reaching a critical value, it is like it is called fracture toughness. So it is this fracture toughness is your material properties. This is material property, and this K or thing, it is like you are applying something, and then when it reaches this critical limit, then it will fracture. So this is your fracture toughness. So fracture toughness and toughness are different thing, right? This is at the totally two different concept. Now you understood this? Yeah. And then what is hardness?
hardness or maximum energy absorbed before failing when we apply the stress.
Maximum energy applied before
Absorb.
failing.
Yes.
Is it hardness? What are the different kind of hardness you have heard about?
Yes, sir. We have had we have had about the measuring of hardness, like weaker hardness or
Yes, and
Rockwell hardness.
yes. Okay, so what you have told that the maximum energy absorbed before failing.
When we are applying the stress, basically, then
Uh,
before failing, how much it can be observed.
so what do you mean here by failing?
Uh,
Means when you
mm,
are measuring the hardness, are you destroying your sample totally, or are you fracturing your sample?
uh,
Have you measured
sir,
hardness in your lab or?
सर यस सर वही तो करते थे मैंने मतलब जब रोकेबल हार्डनेस में या तो फिर विकर हार्डनेस में सैंपल को रखते थे और ऊपर
Mhm.
से आइडेंटिफायर को अप्लाई करते थे तो वो मतलब हम नोट करते थे कि किस जगह पर मटेरियल पर वो मतलब कितना मतलब वो जो आइडेंटेड अंदर ऑब्जर्व सॉरी
Indentation.
इंडेंटेशन हुआ है और वो
हाँ,
नोट मतलब वो जो है स्क्रीन पर दिखाता था मतलब
yeah.
इतना फोर्स पे ये जो है इतना अगर स्ट्रेस को
So
अप्लाई करेंगे
so basically you are making an indentation on your sample. So is
यस
it
सर
means your sample is failing, or your sample is like, is it failing your sample?
नहीं नहीं नो दिस नॉट फीलिंग समझ बियर टू रेसिस्टेंस ऑफ स्ट्रेस
So
ऐसा
what you are
मतलब
doing in case of hardness, you are taking your sample, you are like indenting with let's say there is a different kind of hardness, use different kind of shape of the indenter. So in case
यस
of
सर
Vikas it is a diamond shape, in case of
यस
Binel it is a ball shape,
बॉल से
right? Yeah. So basically you are making indentation here, right? So in case of Binel it will be a round kind of semicircular kind of. So you are deforming your material or your sample locally. In the very localized region you are deforming, you are not deforming the whole sample, or you are not fracturing your sample. So now we can say what is the definition of hardness.
सर मैक्सिमम डिफॉर्मेशन कैन दिस मटेरियल बियर
No, not maximum deformation. Hardness is basically the resistance of resistance of your sample for the localized plastic deformation. It is a resistance of your sample for localized plastic deformation. You are not giving maximum means load or maximum energy, you are not applying. There is just some kind of standard load is there for depending on the either it is a hard sample or soft sample like this. So it is not like you are giving as much as load possible till the sample is getting fractured, right? There is a standard load is there. Okay, so you are applying that load on means onto your sample, and then it is creating indentation, and then you are measuring the diameter or dimension of this indentation, and then there is a different formulas for Vickers hardness, for Binel hardness, and then you are basically calculating your hardness value, right? So it is basically that how much load you are applying, and because of that what is the dimension of the indentation you are getting. So basically this ratio is gives you the hardness. So hardness in the physical sense, it is basically uh, the resistance of your sample for the localized plastic deformation. Now this plastic deformation you can give by various way, like one is the indentation, another is also the scratch. If you are scratching your sample, na, this is also defining the hardness. If you are taking a very hard material, and then if you try to scratch it, so it will have a much resistance against that scratching, right? But if your material is soft, it will have a less resistance for the your scratching, right? Let's say you are taking a aluminium sample, and let's say you took a nickel sample. Okay, in aluminium you can easily make a scratch, right? But in case of nickel sample, you won't be able to make a scratch so easily, right? So
Mm.
different kind of hardness are there, which depends on which way you are following, like that Vickers, Brinell. So this Rockwell, okay. So this hardness basically measured by the indentation technique. So that's why it is those hardness are called the indentation hardness test. So there is similarly for I think for the uh, minerals or like this, they use Mohs hardness test around like this. So there is a different kind of hardness terms is there in which way you are determining. So in that way they are basically termed. But the main concept is it is the resistance of a material for the localized plastic deformation. In this case, you are not fracturing your sample, or you are not applying a maximum load that it can be withstand, right? So now you are clear about this, right? What is hardness?
Yes, sir. Sir,
So
one thing,
yes,
when this is a localized plastic deformation, so is it good, yeah, okay to say the hardness of the particular sample, because we are saying this is the hardness of the material, yeah, sample, and we are
mhm,
testing at a particular point. So it
yes.
is a good to say this is the hardness of the same material, yeah, hardness of a particular point of this material.
No, that is like now you are going into some different thing. Like now, let's say you have a sample, and there is a two type of hardness is there. Means in case of Vickers also, the, when your size of the indentation is large, so that means let's say in your sample there is a various grain will be there, right?
Yes, sir.
So it might be a single phase or two phase. If it is a single phase region, then you can say this is a overall hardness of the sample will be almost same. But if it is a two phase region, let's say this red one or the one different phases are there. Okay. So now, if your indentation size is such that it is covering both the red and that green grain, so that means you are basically averaging the hardness from this region. That means it is taking the hardness value from both the phases. So this
Yes, sir.
average hardness is then you can term it as a hardness of your sample. But if you
Mm.
go for the micro hardness testing, in that case you that size of the tip or that the indenter you are using, it is very small. So then you can go at a higher magnification, and you can particularly take the indentation at a single phase itself. Let's say you are taking a hardness for this phase only. So this is micro hardness. So in this case, this hardness will be only of this phase, not other for the other phase, or not for the whole material. So, in which technique you are following, or you are measuring the hardness of your sample. So then, in that way, you have to express. If you are measuring it for the bulk sample, and you are creating a large amount of indentation or larger size of your indentation, then you can say it is the average hardness of your sample. But
Yes,
if you
sir.
are doing micro hardness and you are taking at a particular phase only, then that hardness will be the hardness of that phase only, not for the whole material.
Okay, sir. Okay.
Okay. So now everything is clear for this
Yes.
question.
Yes, sir.
Toughness, fracture toughness, resilience, and hardness. All four terms now we are familiar about it. What are the differences between this? Anyone has any doubt? So in this question, that ability of the material to absorb energy when deformed elastically. So we found that the answer is resilience. Other terms are the different thing, which I already have explained. Right. So if anyone has no doubt, then I can move to the next question. So should I move?
Yes, sir.
Okay. Okay, so now this is the question number 33 of GATE 2014 Metallurgical Engineering. The question is, what is the theoretical requirement of air in meter cube at standard temperature pressure for the complete combustion of 100 meter cube at STP of a fuel consisting of pure methane, pure CH4. Assume that air contains 21 volume percent of oxygen. So anyone want to approach how to solve this question? This is a very simple question. Just you have to do the mass balance and you have to write the equation, and then you have to do the mole balance. Then we can easily proceed with this. Can anyone guide me how to approach this question? Anyone? Devendra, Manikam, anyone? What what will be the first step to approach this question? What should be the first step? We just read the question, then we will get. So what we have to calculate? We have to calculate how much air is required to burning the fuel. And what is the fuel here? Fuel is methane. So basically we are burning the methane. So if we burn the methane, what means with which component or with which element of the air it will react? With oxygen only, right?
Oxygen, oxygen.
Yes, when something is burning, so it will only react with the oxygen which is present in the air, and then it will give rise to the oxygen after oxidation which product will form. So basically, let's say this is your container where CH4 is there. Now your air is going in this way, and then it is burning. So it will react with the oxygen which is present in the air. So what will be the then chemical reaction? This is CH4. It is reacting with oxygen. What will be the product?
H2O,
Yes, it
CO2.
is states that for complete combustion, right? Complete means it will form CO2 plus H2O. It will not form CO or any other intermediate kind of like CO means if it is forming CO, that means it is not completely that combustion is not happen completely. So it will not form CO. So it will form CO2 because it is state that it is for complete combustion, right? So in the question itself, every data are given. So you just have to read the question properly, and then you can just simply approach this question. Now we have written the equation. Now we have to do the mole balance, right? Then only the equation will be complete. So in the left hand side, carbon is 1 mole only. Here also 1 mole. Hydrogen 2 mole is there, but hydrogen here is 4 atoms. Is 4 atoms of hydrogen is there. So we have to multiply it by 2. So now hydrogen becomes 4, right? So carbon and hydrogen are
Yes, sir.
balanced. Now oxygen becomes 2 here and 2 here, means total 4. So that means we have to multiply it by 2. Right? Now our equation or reaction, this reaction is now balanced. Now we have to find out how much air is needed. So for that, and that air is air is basically giving the supply of oxygen. So for that, we have to first find out how much oxygen is required for the complete combustion. So let's say, so now we can see from here, 1 mole of methane is reacting with 2 mole of oxygen, right? It is reacting with 2 mole of oxygen. Yeah, 952.38. Yeah, you're right. So 1 mole of CH4 is reacting with 2 mole of oxygen. So what will be the volume at standard temperature and pressure? Volume of 1 mole of gases is 22.4 liter or 22,400 meter cube of CH4 is reacting with 2 into 22,400 meter cube of oxygen. Now we have 100 meter cube of fuel. So how much oxygen will be needed? 2 into, so it will be simply 200, right? So we'll need 200 meter cube of oxygen for 100 meter cube of CH4 to burn. So now this 200 meter cube of oxygen is coming from the air, right? It is coming from the air. So let's say in air it is 21 volume percent oxygen is present, right? So let's say we need X amount of air. So in the X amount of air is required, how much amount of oxygen will be there? X into 21 by 100. This much of oxygen will be there in the X meter cube of air, right? And this is equal to 200, right? So what will be the X? 200 into 100 divided by 21. So what will be the answer then? Right? Not mole, meter cube, volume.
Yes, sir.
Yes. So everyone understood? Because
Yes, sir.
so it was a very simple question. Just we have to do mole balance. Even if you don't means write all this thing, na, if you just visualize and if you can directly calculate this answer, means get this answer. Because just you have to write this this equation only, reactions only. And then you can see that 1:2 ratio is required. So easily you can see that 100 mole of CH4 means 200 100 meter cube of CH4 means you need 200 meter cube of oxygen, and that 200 meter cube oxygen will come from the air. So it will be simply 100 into 100 by 21. Just you have to multiply it and then simply you will get. So very quickly you can solve these questions. So anyone has any doubt on any of the question that are solved today? So today we basically covered three simple questions. One is related to the tensile uh, specimen which is deforming at a constant cross-head speed, and we had to find out the initial gauge length L naught. The second question was this one. Here also I explained that what is the toughness, fracture toughness, resilience, hardness. What are the difference between these four terms? And this is the third question of today. So anyone having any difficulty in understanding any of this question, or if you have any doubt,
Sir, please.
yeah,
Hello. Sir,
yeah.
please repeat the fracture toughness definition.
Okay, fracture
I have
toughness.
confused. Yes, sir.
Okay, fracture toughness is basically like fracture toughness. Okay, well, let me first tell the definition. So definition is basically fracture toughness is a critical stress intensity factor who- which for which your the crack propagation rate will be very rapid and which will lead to the fracture. It is a critical value for which your fracture will occur. Like so, it is like if you just visualize from the this diagram also, na. What is fracture stress? Fracture stress is when your sample is getting fractured. Similarly, for fracture toughness, it is like if your sample have a crack or sharp crack. Okay, so fracture toughness is
Yes,
basically
sir.
tells you how the your crack will propagate. That fracture toughness will basically test. Means- Now, if you have a very sharp crack, na, so then if you load this sample, okay, it will be better if I just write in a blank page. Okay, just a minute. Okay, so let's say this is your sample. It has a very sharp crack. That's the edge crack. Now, if you load this sample, so this is sigma. So your stress at the very distance from the crack, the stress will be like that stress line will be a straight line only. but when this stress line comes to the near the crack, it will bend because of the unavailability of the material or unavailability of the path. So what will happen? Large amount of stress will get concentrated near your crack tip. So that means in this case, your deformation will be concentrated near the tip on itself. So near the crack tip itself, here the deformation will be concentrated. So initially your tip was like this. Now when you are loading, too much of stress will be concentrated here. So let's say this is the distance from the tip x. So if the stress we are applying sigma, so that means at very far distance from the crack tip, your stress will be sigma, right? At a very distance, your stress will be sigma. But as you are approaching towards the crack, what will happen? Your stress suddenly increase. That stress because of the stress concentration. What is happening here? So suddenly your stress will increase near this point or very near at the tip of your crack. So it will here the stress will be sigma max. That maximum stress it can reach. And here the stress will be sigma, which sigma you are applying. So because of that, what will happen after some times? Now your crack is sharp, but your stress is higher at this point. So as your that sigma max, this value, if sigma max, if it is greater than sigma of your yielding or yield strength, what will happen? Near the crack tip, it will deform, right? Plastically, it will deform because
Yes,
he-
sir.
let's say you are applying as sigma. This sigma is less than sigma yield. Okay, so your bulk means at the bulk that material will not get deformed plastically because there the stress is very less than the your yield strength. But although you are applying stress which is less than your yield strength, but because of the stress concentration, the at the crack tip your stress is too high. Okay, this is given by this ratio, that is kt. I have told the stress concentration, that is sigma max by sigma. This is stress concentration, this is not stress intensity factor, or this is not fracture toughness. So now because of this your crack tip will blunted. Now if this sigma max is way too high, that if the sigma max is crosses even crosses the your fracture means sigma fracture value, then what will happen? Then again here will crack will generate because it will fracture this localized region. So again your tip will be like very sharp, right? So your tip will be very sharp again. So again this thing will happen. Again your tip will get blunted and again this will get sharp. So like this your crack will uh, propagate. Okay, so this is in this way that your crack will propagate. Now this sigma max, it is related to applied sigma, right? What is the sigma max? kt into sigma, right? So now let's say if you applied the sigma, applied sigma is you are increasing your applied sigma, so it will reach a certain value when what will happen? This crack propagation rate will be very rapid. Okay, so that crack propagation rate will be very rapid so that it will lead to a fracture. So at that time that your stress intensity factor is actually given by y into sigma pi a. Now when this sigma value is reaches a critical value, then this stress intensity factor is also termed as stress critical stress intensity factor, that is KIC. It will be y sigma root over pi into AC. So this critical stress intensity factor, it is called fracture toughness. This K or stress intensity factor is related to sigma or like this. This is your applied sigma. So it is related to your sigma by this equation. If you read this topic in the data, it is also mentioned very well that Griffith criteria is there and another different criteria is there, which basically showed this how this formula is coming, how this lesson is coming. So you can go back and then check this concept, like how these things are coming, because these are related to very means that derivation is a quite in the book it is very simple. So you can just see. So this is the relation between the sigma, your applied sigma, and the stress intensity factor. Okay. So this stress intensity factor, when it reaches the critical value, then it is called fracture toughness. So that means at that critical value, that your crack propagation rate will be very rapid and which will suddenly leads to the fracture. Okay. So if you see the definition, it is a critical stress intensity factor when so at that time your crack propagation rate will be very fast and it will suddenly just propagate and it will cause fracture of your sample. This critical stress intensity factor, this is called fracture toughness. So what will be the unit of this unit of fracture toughness? On what thing it is dependent? Sigma is Pascal or something, Newton per meter square you can say, or a megapascal. So in this case, so it is Newton per meter square, and this will be in unit of A is meter. So root over of m. So it will be Newton per, okay, meter to the power, uh, or you can write in terms of this is in terms of Pascal also, or in megapascal into meter to the power half, or you can write Newton per meter to the power 2 minus half means how much it is, 3 by 2, right? So
Three
generally it
by
is, yeah, generally it is written in this term, megapascal, or it is megapascal into meter to the power half. So this is in this unit it is written. Now what is the unit of toughness? Toughness is what? Toughness is half into sigma into epsilon. So unit of sigma is megapascal into unit of strain is, it is unitless, right? So toughness is also megapascal. This per unit volume also you can say. So that's why it is energy per unit volume or joule per meter cube it is say. So these units are also different. So this toughness and fracture toughness is a different thing. Fracture toughness is when your sample have crack, and it basically defines how your crack will propagate, and what is the resistance, means that what is the critical stress intensity factor for which your crack propagation rate will be very rapid. So, and fracture toughness is when your sample is plastically deformed and then it fractures. Up to that point, how much energy is absorbed. So this is your fracture toughness, and this is your toughness, and fracture toughness is different. So now you understood it.
Yes, sir.
Okay. And any doubt regarding any other question? Or from the previous live session also, previous question, if you have any doubt also, then you can also ask me. Everything clear? Are you
Yes, sir.
guys practicing question from somewhere else also? Both of you are in fourth year recently, right?
yes,
Currently,
sir.
yeah. So are you guys also practicing other miss question from any other uh, means solving the different questions also? It will be more helpful for you if you guys just solve as much as question possible. Then
Means, sir, you are saying that a question from the other institute, yeah, yeah.
Yeah,
from
from any
question bank.
textbook also in the problem section there is a lot of question will be there. Even you can solve the other like this kind of there is a, if you find any objective book for metallurgical questions there. So these questions also you just can solve by yourself. So as much as question you will solve, na, that will give you much more confidence and also help to increase your speed because for gate speed is also important, right? Now here actually I am explaining all the thing and then I am solving the question. That's why it is taking a bit time for solving this three question. But in gate exam you have to solve this three question very quickly, if possible within 3 to 4 minutes itself, right? So then you have to note down few of the important formulas and all, right? So like here also when I am covering this these questions, so you just try to note down the important formulas, right? So like here as that strain rate, how it is depending on the cross head speed and L naught. So these few is important formula if you just remember, so it will be helpful for you guys also.
Thank you, sir.
Yeah. Okay. Okay, if no one has any doubt, then we can close today. So we'll
Yes.
meet again on the next Friday.
Okay. Thank you, sir.
Okay, thank you all.